So we have a little bit of a section here about the physics of superconducting qubits. I will probably not go formula by formula, but I will give you a little bit of ideas how to troubleshoot when you get in trouble. So Schrödinger equation, Nielsen-Chuang. Then we have some text that we will skip, and this is also just quantum mechanics evolution, so we didn't really need to spend too much time on this. Time-independent Hamiltonians here, some talking about stuff, that's the overview, okay? And the next paragraph, sorry to the authors, because I mean, clearly they wrote this because it meant to convey something, but this is for readers that are reading on their own. I'm only giving the overview. So, so in the overview, we want to just understand what is where, and then individually when you're reading, you want to spend more or less like the timings that I said. So reading the stuff carefully. In this section here, there will be something which is interesting, and I will hint you towards that, this potential and kinetic energy of superconducting qubits. And the review is written well because it says to understand the dynamics of superconducting qubit circuit, we will start with the classical description of the linear LC circuit. And then what we will see is that there is a lot of talk about quantization of LC circuits. And a superconducting qubit is a quantization of a nonlinear classical oscillator. That's the regular stuff. So I will scribble it here because that will tell you why you need to read all of this stuff and why it's worth your time. It's worth your time because it will put you in a position to understand the quantization of nonlinear harmonic oscillator. Okay, why? Because you will see always for transmons those kind of pictures where a harmonic oscillator would look like this, and every level is spaced by delta omega. While in this review, we'll see a lot of talk, because this is really essential for superconducting qubits, is that I actually happened to draw it kind of like this, but this transition here, delta, will be different than the transition to that level, which is delta prime. And to get it, you take a linear harmonic oscillator, a regular harmonic oscillator, you add a nonlinear element. This is called the Josephson junction. Let's see if the Josephson junction appears on this page. Not yet, because we are not quantizing on this page yet. Okay. Let's see. Okay, maybe it's written better than me just skipping ahead. Huh? Okay, so yeah, let me just give a bit of an overview how to look at this kind of stuff here. This equation here is quite important, and basically it allows you to transition from like maybe voltages, which is something that you can apply with some voltage source. Okay, so you would be adding some voltage from outside here into a node of some maybe quantum circuit here. And quantum circuit not in the sense of like gates and so on, but like circuitry of how to put together superconducting wires to create superconducting qubits, okay? But anyway, the next equations that you see are the kinetic and potential energies of a regular LC circuit. And basically what you will see later is that capacitance in those physical hardware circuits involving superconductors, this capacitance is sitting on the Josephson junction. So the Josephson junction is something that will be nicely explained later on, but this is the key element that is basically, you should think of this as the source of the nonlinearity. Okay, so I'm skipping ahead many things, but what I'm giving you is a little bit of an overview how to make sense of this and what's the role of the individual things somewhere. Yeah, so basically the Josephson junction will add nonlinearity in the sense that this potential energy will not be a quadratic function of the phase squared, which you define here. So the detailed reading is about understanding more or less more deeply this, but if you understand where things are, it's a bit easier to parse it. So phi squared gives you a linear harmonic oscillator, but if you take cosine phi, this is a nonlinear harmonic oscillator. And the way you can think about it is that if you have some angle phi here, yeah, and you have a pendulum in the gravitational field here, then it's a nonlinear harmonic oscillator of a similar type. So basically the height of, you know, how the pendulum is pulled, depending where I put the phi, it will be either sinus or cosinus. Okay, and when we linearize the cosine phi is the identity minus 1/2 phi squared. Okay, so basically there will be always a minus in front of the cosine, so that after the linearization of the cosine, I will have a positively defined potential energy. Okay, so this minus, that's some hint that I'm giving you if you ever read it carefully. Okay, so that's some overview of the formulas where they are positioned here. The next thing to say without telling you much about what they are doing here is that they usually prefer the Lagrange description, because the Lagrange description allows you to treat nicely things that appear later. And things that appear later is something where I want to scroll in somewhere here. I think I was seeing it. This gauge invariant phase. Which is something that is useful when we are driving a qubit. So when I have a superconducting qubit here, and I'm driving a voltage source here, then at this node, I will be imposing a little, some drive on maybe this phase variable, this flux variable, or what you want to call it. Okay, and I will be pulsing their voltages. So my voltage source here as a function of time will be some function like this, which will be adding time-dependent terms into the Hamiltonian. So this Hamiltonian will become time-independent, and to do it carefully, it's apparently useful to go to the Lagrange description. That's some overview here. So you will see Lagrangians. But if you don't like Lagrangians, you don't need to be very scary, because it's a quadratic function for now. Yeah. And those Lagrangians will give, yeah.
I was just going to say, we were looking at a recent paper that was really interesting in this regard. Obviously, this is just like if people are interested in this and kind of want to look at some more recent stuff, which is interesting. One of the key things that a lot of these superconducting qubits have, right, is that they have to have at least one quadratic term, because essentially, like, in order to like solve the Lagrange, like essentially you want some kind of kinetic energy term or something that you can liken to kinetic energy term to make the solution a lot more tractable. So you can have one nonlinear term, but it's harder to have both. There's this recent paper that went out of the archives, which I'll drop in chat now, which addresses this. And so it's also potentially this, if you're interested in this stuff, this is also good to look at, I would say.
All right. Okay.
That is not the archive link from, sorry.
Yeah, but there will be the archive link. Yeah, okay, so that's a nice paper that I was maybe omitting, but so symplectic geometry is kind of not something that we are entering so much in those tutorials, but we did a little bit of like some outlook towards maybe going a bit more geometrical. The archive link for what Nick is saying you have here. And this circuit quantization is actually very interesting for this whole business. So maybe let's keep it at that, but it's kind of both nice that it's possible to do it with a fair degree of generality. And it's also driving the field forward that it's possible to do it systematically. But part of the field is, I guess, to do it systematically, and maybe that paper would fall into that question. And yeah, the standard thing is that we start with the oscillator, but then how we add the nonlinearity is, I guess, something that that is, I don't know, to be explored. Or maybe if I do it like this. I think it will be cited here. A paper that I really enjoyed was in Quantum, and it's about a package called SQ circuit. And if you want to read a very abstract, more field theoretic paper, that would be the paper maybe that Nick is suggesting, because there's symplectic geometry quantization together, so it will give you some mathematics probably. Sorry if the paper is not about that. And SQ circuit is giving you the solid physics, and is written by people who know kind of the outlook for applications. And is directly linking to a package that you can install with pip and just run in your Python notebook to quantize some transmon circuits, fluxoniums, and so on. So I really enjoyed SQ circuit, and I like the comment because I was also thinking about this kind of quantization stuff. Yeah. It's just like an area where one can branch out and then study a little bit more in detail. What you will find here is just the overview, just saying like, this is how it's done. And basically you see it's fairly complicated because it's like one column just to set everything up, okay? And okay, at some point the discussion is ending, and no, I think this is doing more than just discussing this, because no, yeah, so Cooper pairs we still have here, but those Cooper pairs will be important later. Still on this page, we are talking about the quantum harmonic oscillator. This is an important section telling you about the vacuum levels of the harmonic oscillators that we would have if we wouldn't have a Josephson junction. But basically, you need to go through it. You need to familiarize yourself with the notation. You need to kind of link with your mental nodes in your head to understand how it's linking with your knowledge of harmonic oscillators. Then they will nicely explain to you what is the frequency of the oscillator. They will kind of explain to you what are the level sets of the oscillators and so on. So you look at all this stuff. And then you come to 0-point fluctuation operators, which is an interesting discussion. It's worth looking at this. And I think here I would refer to Gervin's notes if you want to know more about this. It's not a very simple thing when you encounter it on the first time. I'm not trying to explain today. Yeah, I'm just saying some things are sometimes just something you should accept, and sometimes it's realistic to dig deeper a little bit. And sometimes something can be a rabbit hole where you will be reading for forever. I think this is described, if you're reading Gervin in parallel, then this is something that that still can give you a little bit of insight about the impedance. So when you will be reading about impedances for those qubits, this stuff comes into play. And just to tell you, if you read it, otherwise more or less keep reading, because we didn't get into the interesting business yet, but we are on page number 5 and we get to see our our goal, which is the transmon qubit. Okay, so somewhere here, let me see if I will be able to point to you the definition here. Just to say, this section here tells you what exactly goes wrong if you want to build a qubit using this. So basically, if I have my system initialized in a 0, which means just let the energy escape and you will be in the ground state at some point. If I want to excite here, it might happen that the system will absorb 2 photons of an excitation and suddenly I will excite into the second level. And at some point they say natural limitation in its applications and so on. If we scroll down, I was already seeing some formulas, the transitions, frequency transitions between those 2 levels. So let me just write it down. So this is omega q 0 to 1. And this is omega q 1 to 2. That's this kind of notation in pictures, yeah? And because of that, it's harder to do control. And usually people don't talk too much about how to keep a harmonic oscillator. We just say, okay, let's try to bend up this harmonic potential here and basically create a situation where there is some unharmonicity. So if I will scroll down, there will be some equation, some outlined equation at some point. Where we will see the definition of the unharmonicity. And that was maybe in line. Okay. So sorry about that. I'm just searching. Here's the alpha. Okay. So this is important, something where you're reading, you're like, oh, this is the crux of everything that I was reading about. That's kind of this unharmonicity, which allows me to drive at the frequency of this transition. So basically, I would be driving in some way, so to speak, at the frequency of that transition, which means it will be detuned, so it will be off resonance to absorb it to get to a higher level. That's roughly the idea. Okay. To understand it quantitatively, you just read the paper, okay? So I'm not saying more than this here. Okay, so let's look at the transmon. I mean, you will see it properly explained line by line in the paper, but just some comments. There will be a single degree of freedom. It will be in this paper denoted by phi, okay? And that phi will be oscillating. So basically phi dot squared is the kinetic energy. Phi squared would be the harmonic potential, and cosine phi with maybe a minus somewhere, or actually here we have a sine phi, sorry, for the Josephson coupling. Yeah. So no. Here is the Hamiltonian. So instead of having phi squared, you should note that there will be the cosine with the minus, exactly as I was saying. Okay. Yeah. So that wasn't incorrect completely. Yeah. So basically, this is a highlight. So yeah. And maybe should make you be like, whoa, so cool. Yeah. When you get to equation number 16, worth your time. So basically, this is created by those parameters here. EJ, the Josephson energy, we should find that at some point there will be some formula. Can we find the formula for EJ? Well, it depends basically on properties of this Josephson junction, and I don't see it quickly here. Actually, in the paper, it's more or less explained. Oh, so here it's EJ. So you have this critical current through the junction, which is parameterizing some variables, dynamical variables of such a nonlinear oscillator. And basically here you have phi 0, and if I'm not mistaken, phi 0 will be defined using those 0-point fluctuations. But this phi 0 is now for the nonlinear oscillator, but that's kind of the relation. For the harmonic oscillator, those 0-point fluctuations are easier to understand. So yeah, I'm not able to point you exactly where this phi 0 is defined here, but it will be defined somewhere. Let me clean up a little bit. So not phi squared, omega squared, cosine squared, so cosine phi 1 minus 1/2 phi squared. Okay, approximately. And here we have omega q1 0 to 1. Okay, so basically what you need to learn to accept, and it will be easier to accept after you read the full paper, but there are those parameters which are more or less fabrication parameters, and the paper will explain to you how to design those parameters and so on, but at the end of the day they will be fixed in a given parameter set, and that's it. What is more important is given those parameters, they translate to the unharmonicity here, that there's a different transition rate between those qubits. That's more or less your mental map. Going from the hardware, where the hardware is, for example, giving you this critical Josephson current and so on, the capacitances, all this stuff is hardware. You kind of build up the stages of having a more abstract model. Once you have this abstract model here, you can start doing quantum control and so on. And at some point you go to superconducting circuits. Okay. So cleaning up here a little bit, but that's the pathway. Yeah. So I will write here hardware as in fabrication. That fixes those parameters. Those parameters fix the Josephson energy. Okay. And the Josephson energy, again, you're spending maybe half an hour to read through. But the Josephson energy, okay, actually we had it upstairs there. Let's scroll up, sorry for jumping around so much. But this Josephson energy is somewhere here. And that means that this is the unharmonicity here because of this. It's roughly a harmonic oscillator, but whatever is not the harmonic oscillator is kind of decided by this EJ. Okay. That's our EJ here. Yeah. And once we have this, so one fabrication, two physical parameter, three physical model, for this detuning it's called, or unharmonicity. Once we have this, we have 5 qubits, and that gives us maybe some performance questions. And that maybe gives us some also operation on qubit. Yeah. Basically, those are the questions that are going forward. And then I will draw it like this. I need some space. So dot, 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 a long pathway. And then basically running quantum gates. Okay. Still a bit longer road ahead, but basically it's a full roadmap. That's the nice thing about the paper. So today we are skipping the full page. This will be always interesting, important in transmons. So spend time on trying to keep track of what's happening to those frequencies. And if a paragraph tells you more about the meaning of the stuff, then you already gain something. It's not obvious to read everything line by line and understand everything, but you should be reading line by line, at least on first reading. There's no other way around it. I mean, the way I'm skipping around here, I mean, if you would be reading like I'm skipping today, I mean, not much that you will understand that way, right? So you will see that people will be talking about relatively weak anharmonicity. Okay. Actually, maybe quotation marks on weak. And what is meant by this is this expansion where you get some sort of single mode 5-4 theory. There's the anharmonicity, as we were saying, defined here. That's important here. And basically what is also important, that's more or less like the kind of summary of the work that you were doing, is gives you more or less the transition frequencies, and megahertz is actually not so far from kilohertz. So like those kind of oscillations is like almost getting to some acoustic range at some point, right? So it's still an engineer's guide, so it tells you some frequencies for transitions. Yeah. So basically, what does it tell us? We have 100 to 300 megahertz anharmonicity, which is kind of the detuning. So basically, that's kind of what should be protecting you if you don't have frequency crowding from exciting higher levels. And this omega q is more or less the frequency that you need to go from level maybe 0 to 1. Okay, so that will be some oscillation pulse that you need to add from outside, and that will be the discussion for how to do the interactions later on. Okay, then there's stuff that you should probably read because it's a good exercise, but it's telling you more about this anharmonicity, and here you can read a little bit faster. Yeah, because it gives you a little bit of a physics intuition about this anharmonicity, but like you don't need to overdo on this. Yeah. So if this is not so understandable, it's basically you're not really understanding like what makes the physics stick of protecting those transitions a bit and so on. That's all that you're missing. But if you're buying it, if you're buying this picture here, yeah, then you're more or less fine. Yeah. Good. So the fun starts with the split transmon. The split transmon is a very interesting construction. The formulas, as you will see here, get a little bit more involved. You see that there will be phase 1 and phase 2. Basically, what we should see in the picture is that there's a different flux over those two nodes in the circuitry. So basically, when I have some circuit, I can consider nodes, and then you ask what's the kind of flux over that node, and there's phi 1, phi 2. A regular transmon has only one variable, so phi 1 or phi. A split transmon has two. Okay, phi 1, phi 2. Okay. They will explain to you here that there is something called fluxoid quantization condition, which actually fixes the difference of phi 1 and phi 2 to be integer multiples of 2 pi chi and some offset. And this offset is the external flux that I could basically couple here with some oscillator, or either maybe, I don't know, some oscillation element, and that will add you this external flux here. That is very cool because it allows you to shift the flux difference, and that allows you to tune the qubits. So so you see EJ is tunable, and I say it here. We eliminate 1 degree of freedom and treat the squid loop where we have two transmons, you have like a symmetric transmon, but two Josephson junctions, sorry, getting tired. You have two Josephson junctions, that's a single transmon, it's called a symmetric transmon. It still has 1 degree of freedom because of this flux, so it's quantization. What I'm highlighting is more or less the key things to interpolate later, you know, when you read. And what this allows you to do is to tune the difference between those phases. Yeah, this is a key component there. Okay, very good. And how does it happen? This phi e here, you don't see because I'm scribbling over it. So phi e here, phi e is the external flux divided by whatever this, I don't know, 0 points level or something. Don't remember the exact name. So if I'm tuning the external flux, I'm also tuning the overall prefactor of the cosine of my transmon. So I'm changing something in the transmon. Okay. Okay. So changing phi x, controlling qubit. Okay. That's roughly the mental map. Of course, reading all the details means like how to do it exactly. I'm not even trying to tell you how to do it. Okay, this figure is fantastic. I will not say too much about it, besides that it's worth your time to kind of inspect those dots here, investigate this and compare to the regular transmon. It's described quite nicely. You have a little bit of like an encyclopedia of different structures that you can do. And that should be stressed. I think they stressed it quite nicely in the paper, but I don't know, I'm kind of presenting today and it's a bit of an overview tutorial. Basically, Nick mentioned also this business of quantizing circuits. So the idea is that you can basically say, okay, let me have a Josephson junction here, a Josephson junction here, maybe here as well. And then let's say, let's put them in line. I don't know, let's put another Josephson junction here and so on. That's kind of the things that you can do in some engineering software. And if you have automatic fabrication, you could try to say, let me have this kind of qubit. And what I described here is kind of a triple shunted flux qubit, or you could say that maybe it's already in the limit of a fluxonium. So basically the idea is that's the big advantage of superconducting qubits, is that you can relatively quickly request and get delivered qubits that have new properties and so on, right? So that's kind of maybe the overall meaning why you shouldn't view this as hair splitting and like different qubits or whatever. That's kind of the joy of this. Yeah, this is good stuff. That's a big advantage of those qubits, that you can create new species of qubits and explore in hardware new properties of qubits. Okay, so almost done here. Yeah, so this will be talking about asymmetric transmons. I really like the exposition here, that it was kind of telling you more or less what you're gaining, what maybe you're losing, if you're losing something, and so on. So I remember that this section was quite nice to read. And usually those summaries at the end of individual sections, they are pretty good. So when you see the end of the section, you will be already, you know, but being home for one reading or something like this. So I won't be summarizing this too much, just giving you an overview of what you will find, and then try to read and try to navigate between those things here. Larger anharmonicity will be building on the other anharmonicity, but you will kind of see certain things, and it's just like maybe half an hour, just read through. If it's important for you, read it again. If it's not important for you, just try to remember what you understood, which means that there are ways of engineering adding more Josephson junctions so that you have better properties. More or less, this section tells you how exactly this has been realized, and of course it's an achievement of several papers. But that's how fast superconducting qubits developed. Like, single kind of qualitative idea for improvement is several papers that are really exciting and was advancing the field and so on. So it was advancing at a rapid pace, and then you read through here and you kind of can appreciate what was going on there. But that's kind of also making us optimistic about the possibilities of really engineering stuff. Okay, so that was superconducting qubits, more or less, the different species of them and so on. So I think the point of the authors here is that as a quantum engineer, you should be aware that you can engineer new qubits. You should be aware of the engineering solutions, how to create the qubits, which ones have which properties and what kind of parameters you can have. I see here 0 pi qubits and so on. There's different ones, and that's kind of the tough thing that maybe in physics we don't do so much as in engineering, that you know encyclopedically all the things. But as a physicist, there's not so many of them, and you kind of can enjoy the physics of them as well. So depending on what's your priorities, you can take different perspectives on it. We are on page number 9. And I think until this stage, you probably should have had a lot of fun. If you didn't have enough fun, you should maybe read a little bit faster and trust that the reading will be quite good. I think it's worth continuing. And I will be stopping here today. And the stuff that we will continue with is how to make couplings. Yeah, so all those circuits here. Yeah, and once you have couplings, that's what I was basically saying, that maybe Z tensor Z is a gate that we would like to have, and depending on which kind of coupling you have, you might be going towards those interactions between qubits. Yeah, so that's the work ahead. Yeah, so what else is there? If you're reading fast, you might be able to finish section 2. Okay, and then coupling axis, and you will see here those kind of Hamiltonians. The Hamiltonians are maybe not so easy, but if you're able to understand more or less how this comes about, then you're in game. And then this section becomes quite important. So maybe I will go line by line almost in the next tutorial, because it will tell you about the different frames, and then you're already here in the noise regime. Okay, so we almost covered the 2 sections. Okay, so here again, whoops, this is not looking so good. Here again the title, and here again the archive number of the paper. Yeah, okay,